Hi there, myself Nisek Bhatti, student ID 10141011, and this is the video presentation for the assignment 3 of our machine learning course. This assignment is divided in majorly two parts. Part A, which demonstrate how the 2D conversion works, and part B is which involves training on neural networks on Cipher 10 dataset. So let's begin with the part A. So for the part A, first we need to load the images using the URL, and then just a second, we need to convert the images into the 3D NumPy array using np open and np array. Here it is. Then we need to extract the just one color channel using the RGB channel. Since the RGB channels are equal, so we need to extract that, and let's see the if they are equal or not. So now let's that will give us the one 2D grayscale image. Here it is. Now for the conversion basics, to demonstrate how the 2D conversion work, we first apply the simple identity kernel to the padded image. So let's see if we print the shape. Because of the padding, because of the padding, sizes shape are different. Now we then slide the kernel over the image using the nested loops and applying element wise multiplication and summation. So let's plot the result. Here you can see. Then we have standard conversion. Now here is the function that returns the value which falls under the 255, and define a function to convert the 2D kernel to the image. So this function, as we saw, the padded image and the original image shape were different. This function ensures that the shape stays the same, which is 0 to 55, and also the after applying multiplication and summation to the each element, uh, it stores it creates a new image filled with the 0 to stored in a conversion results. Now for the line detection, to detect the 45-degree line, I have used this kernel, and this kernel highlights the pixel aligned along with the 45-degree direction, and the result clearly shows the diagonal patterns, if you can see. Now for the 135 degree, I'm using this kernel. Again, we apply it using the conventional function and visualize the result. Now for the edge detection, uh, we are using three different kernel. So kernel 1 detects the diagonal edges. Kernel 2 it detects the sensitive edges. And kernel 3 for sharp edge detection, as you can see, using kernel 3. Now this was the part A. Now let's move to the part B. So part B, we used a Cipher 10 dataset which has 60,000 color images in 10 classes, and the dataset is split into the training and test sets. Images are normalized to the range between 0 to 1, and labels are one hot encoded. Now we are creating a model. So the original model has 5 layers. First is Con2D, then this max pooling 2D, then flatten, then the hidden layer of 128 neurons with the ReLU activation function, and the last hidden layer with the 10 neurons with softmax function. Now let's recompile. Here's the model summary, and here we have custom callback function, and now let's run it. Now let's train the network. Let's do it fit. It's gonna take a couple of seconds, no, maybe a few minutes. Let me pause it. So here we train the model for 50 epochs using a custom callback to print the accuracy for every 5 epochs. The training accuracy continues to rise, but after 20 epochs you will see the validation accuracy stops improving and begins to drop, a clear sign of overfitting. So here you can see after 20, it didn't rise, it stays the same, accuracy stays the same. So it's a sign of overfitting. The model may memorize the training data rather than the generalizing the new images. Now let's plot the image. So you can see training accuracy and the validation accuracy. Training accuracy goes, it rises up, but the validation accuracy stays the same after some epochs. So that majorly means the case of overfitting. The model learns well on the training data set, but not on the validation data set. So did the network present a sign of overfitting? Yes, as we discussed, initial pattern after 20 epochs, we saw the accuracy wasn't rising. So we have that. Also write down how many layers this model has identified their types. So yeah, we had 5 layers as we discussed in starting. We have conversion layer, Con2D. This layer applies the filter between the input image and the extract feature. Then we have max pooling layer. This layer reduces the spatial dimension of the feature map. Then we have flatten layer. This layer converts the multi-dimensional into this layer basically flatten the array. Then we have the hidden layer of 128 neurons or units with the ReLU activation function. This helps to learn the complex patterns and the relationship between the features. And then we have final dense layer with the 10 neurons, this corresponding to the 10 classes of Cypher10. And the softmax function, activation function would be the best for that. Now briefly explain the purpose of each layer. So the first layer extract the low level feature like edges, texture that we just saw on the part A, that we saw there are lots of edges and the texture. Then the second layer reduces the spatial dimension as I discussed here, and is decreasing comparison cost and providing some translation in invariance. Then the flatten layer basically converts the 2D array into the 1D vector array, like a 2D into 1D map. It's just basically flatten the array. Then the dense layer helps the complex. Yeah, we already discussed about that. Then we need to improve because we saw the overfitting. So let's improve the model. To improve the performance, I added another layer of Con2D, and this model now learns the feature in the greater depth. Let's see is it true or not. Now let me test it again on the same box. So the neural network has been trained. So as you can see, we have faster learning in early epochs, but then again we see the sign of overfitting and a little bit slightly better accuracy, but not that much. So if we plot the graph again the same way, it's not that different, just a little bit higher accuracy than the before, like a little bit. So if we compare, we have the larger model achieves a higher training accuracy much faster, as we can see, but the it has slightly higher validation accuracy, suggesting better generalization, but still it tends to overfit sooner than the before one. The one before started overfitting after 20 epochs, and if you see this graph, it started overfitting at like 15 epochs or 10 epochs. So those are the, sorry, I went a little bit too far. Yep. So those are the comparison. Now let's add a dropout layer to your model and let's run it. So we have added a dropout layer here. Now let's train the neural network. Let me pause it. So here what dropout will do, it will reduce the overfitting. Dropout randomly turns off the 50% of neuron during the training, and the forcing the network to rely on the multiple pathways rather than just a few. This helps improve generalization and reduce overfitting. So here's how dropout works until it compiles. Let me say. Imagine a classroom where different student answer question each time. It helps everyone to learn better instead of relying just on the top few students. Kind of that. I feel it similar way. So until it, let me pause it again. So the model has been trained. So if, as you can see, we have much higher accuracy than the before. Let me plot the result. So before we had the first model, the original model starts overfitting after 20 epochs, and then we had a bigger model that learned faster but also overfit earlier. And then this model with a dropout layer has more stable validation accuracy and much higher than the before. So as you can see, what dropout layer does, I already explained to you in my words. Another example, imagine a project and one person is working too much and crucial when other person are not working that much. The project might fail. It needs to be teamwork, just like that. All the neurons has to be trained to achieve that. It turns off the few neurons, 50% of neurons, yeah, every time. So every layer learns equally. So that's the dropout layer does, and that's the whole assignment. Thank you for the being patient for this much long. Again, myself Nisarg Bhatti, student 10 14 10 311.